again late as always. I am coming to this next week. So in the MDA 101 we are coming to a, I hope, pleasant though also difficult period. So in this and the next week we shall deal with some applications of the matrix calculus. And the applications I think are quite stunning. So the first one will be the linear optimization, called also linear programming. So I asked, well, I thought I would be you, and I asked the ChatGPT, tell what's the linear programming good for in data science. You see the question is here. And the answer is quite overwhelming because it looks like it's useful everywhere, right? Resource allocation, logistics, transportation, portfolio optimization in finance, supply chain and production planning, marketing, but also machine learning and model training after energy management, etc. So network flow problems. So you see that it's quite a general tool which has been developed, well, from 30s through 50s, and it's still developing. And you will be surprised, or I hope you will be nicely surprised, how easy it is. So at least to understand the idea is quite straightforward. So what are we dealing with? So you may say the important part is just written here on the left hand column. You see that it's a task which is useful if you have some system where the parameters, of course, will form vectors as always in data science, and there will be some linear constraints on those vectors, and the value function will be also linear. So it's a linear optimization under linear constraints. Later on you will see that if it's nonlinear and nonlinear, it's much more complicated, but the linear one is the really useful one. So let's have a look what the problem is. So basically you can imagine, so this very first example in the book tells that you have got some black and white wall painter, and he can decide that he would just work either on small houses by private contracts, or on big buildings by public contracts, right? And he knows what the capacity is. So x1 will be the area painted in the first kind of task, x2 will be the area painted in the second kind of task. And you see there is the first constraint, x1 plus x2 is limited from above by the capacity of the worker, right? So you can't do more than you are able to. Then there are some costs, right? So for the x1 you have some coefficient telling how much of the paint you need to paint the small houses area, how much the big houses areas, and that's for the white color. And then you have the same for the black color. So you have got two unknown parameters, and you have got three constraints, right? So W and B is the limit of availability of the colors. And then you have the value function. So you know that there will be some linear form in the two parameters telling how much you earn if you do this work. And it's just the area of small houses with private contracts can have different price than the area on the public corporations ask, right? So the C2. And so if you draw this, it's just in a plane, so it's easy. So you see what you have here is just you have the three constraints, this one, and this one. And of course we also expect that both the x1 and x2 are non-zero, so you have also these constraints. Now, right, so and in total you see that it's just the darkest area which is the part of the plane we are interested in. That's the area of parameters where the worker could really be. And then there will be the linear form H. And the linear form H, you can imagine that if I take the plane, and in the plane I will take some vector. So I'm somewhere in the plane, I take a vector. So then I have something like a line. And along that line, and the line is given as something like you have a point P and you have a vector, right? You have a vector, and so all the line is given like this, right? And of course because the whole thing is linear, so P in coordinates is again a vector, so H on that will be some constant value H of P plus T times the value H of U. And this one is the decisive part, because you see that it will be growing all the time this way if HU is bigger than 0, and it will be descending if it's less than 0. So if we want to optimize either finding minimum or maximum, we know that along each line it will be as far as possible. So if we start inside of some area here which is of the shape as we had before, we know that the maximum will be somewhere on the boundary. And therefore, actually, it's quite easy to see that the maximum will be in one of the vertices of this, or it might be that the same value will be in two of those vertices. And this is it, because simply it's just there will be just one direction in which the linear form H grows more than in any other direction, and in this direction you see you will hit either just one of the vertices, or you will just have a part of the boundary there. And the same applies in higher dimensions. So in the three-dimensional case, you will have something like a convex polyhedra, so something like this. So you see, it will be just some shape in the space, and you will have the same argumentation that it works. So it's no building of nuclear power plant to see that it must work. But now the problem is how to recognize that each such problem should have a solution, or nearly each such problem should have solution, and how to find an algorithm, how to find it fast. And that's the topic of the lecture this week, right? So let's have a look how it works. It doesn't work. So first we shall stop at a bit of terminology, right? So I will better go for yellow, it's nicer. So we talk about standard maximization problem if we want to find a maximum and we expect that all the x's are non-zero, and we talk about the standard minimization problem if it's the other way around. So we want to find a minimum, and what we face actually is something like a system of linear equations, right? Because we saw that you have simply equations a1, 1, x1 plus and so on, a1 n xn, and now instead of equal you will say it's less than or equal to b1, and this goes on with all the other ones, right? So here the less or equal sign means that we want the same sign to be at each component of the vectors on the left and on the right. That's what it is, and there is a simple way out how to turn this into a system of linear equations. We simply write the thing as A, and then we add a unit matrix, and to the variables x, 1 through xn, we add the so-called slack variables xs. So we always just say that the xs is just the remainder to fill the value up to be 1 in each of the variables, right? So it will be xn plus 1 and so on. So these are the slack variables. And then, of course, because it's the unit matrix, so instead of the equality a times x was less than or equal to b, we get the equality a times x plus unit matrix times the slack variables, which is the same, equals b, right? So this is the new thing. We end with the equation. And on top of that, we do one more thing. We also add one more variable z, and the variable z will be there for value of our function, our linear form, which we want to optimize. And therefore, what we have to write there to make it an equation is we add a column here for the z. So you see here it's just 1 times z, and all the rest will be, well, here it's 1 times z, the first line, and then minus the value of the optimized function. So it's c times x, right? C is the row of the coefficients, x is the vector. So this is what we have. So then there is 0 times the slack variable. The slack variables are just dummy variables. They don't have any impact for us. They don't bring anything. They are there just to be formally at the level of equations instead of inequalities. And so we want to have z equals c times x, and therefore we put here 0, right? So that's how we get it into system of linear equations. And now the whole thing is that we find some reasoning that running just something as simple as Gauss elimination, but in bringing it into the reduced echelon form, if you remember. So the one where you just have something on diagonal and zeros everywhere else will lead us to the solution of the problem. It's absolutely ingenious. It's so simple and it works. So you see, I will go through first a little bit and then we show the algorithm. So first let's talk a little bit about, or let's come back to the definition of the problem. So we have got the maximization problem, which is of the form as I wrote. So all the x's are bigger than 0. Well, by the way, that's not a restriction, right? Because if you would like to work with real numbers as x or real vectors, so without the restriction that all the components are positive, then you simply use 2 values instead of 1, and you work separately with the negative parts and positive parts, and you reduce it to this, right? So you can give it a thought, but I will not stop at that. So you see that it's a times x is less than b. In our convention, this means that each of the components of the 2 vectors on the left and right hand side are in this inequality position. And the minimization problem is I simply swap it. I will take, as we also discussed, so we can either take the convention that our linear mappings are eating columns of vectors and producing the values by multiplying by a matrix from the left, or you can do similarly a matrix multiplication from the right, and then you use the vectors as rows. And that was the difference between the vectors in a vector space and the coordinates of the linear forms. So the linear forms are rows, right? And so I take unknown vector yt. Of course, the number of components in y is the number of equations in the original problem now, right? Because it's just multiplying the same matrix A but from left with a row. And we want to have it bigger than, and now instead of the right hand side b, we here have the coefficients from the linear form, right? So it's the linear form which was optimized. And this is the dual minimization problem to the original maximization problem here, or the other way around. So if we start with a minimization problem, then the dual one will be this maximization problem, right? So again, I draw it as a picture just to notice what it is. It's quite straightforward. You have the matrix here, and you either can multiply the matrix from the right by a vector, or you can multiply it from the left by a row. So here column, here a row. And then I either take this part and say that it's bigger than C, where the original linear form H was sending X to C times X, right? C is a row and X is a column. And or I take this part and I want this to be less or equal to B, right? So B is as big vector as we have the rows here, and this is as big as the row here. Right, so that's it. So let's go on. And now there is a beautiful consideration, so I will not want you to go through the technicalities, and definitely I will not try to explain it. It would be a too long lecture or guideline to reading yourself. So there is the so-called weak duality theorem. So first of all, we know that if we have some admissible vectors, so if the conditions, so the set of linear inequalities has got some solution, so it might happen that it's empty. But if there is an admissible vector for both of the problems, so x is one, y is the other, then we know that the value of the maximized linear form is always less than the value of the minimized linear form, right? So this is the linear form which should be minimized for the dual problem. And there is this always valid inequality. That's the absolute crucial, and it's at a level of an observation. It's just an observation. It comes from blue sky, right? It's just by the setting of the duality, it's automatically true. And you see, this is the whole proof. And then, of course, there is this beautiful corollary, because it says that if there exist admissible vectors for both of the problems, then as soon as you get some values where the values would coincide, I mean some vectors x and y for which the values here will coincide, so there will be equality instead of inequality, it must be the maximum for the first one and minimum for the other one. There is no other way, right? So that's absolutely splendid. And moreover, there is this Strong's duality theorem which strengthens this observation in such a way that not only if we find such vectors x and y with equality, then it's the optimal solution, but it says that if the problem is well posed, so the areas of interest are not empty, then it happens with both of the problems at the same time, so the original and the dual one, and there is a optimal solution then. So you see, and actually it looks like this must be a hell of proving this, right? It's not true, because the rest is proved by finding an algorithm, and that's what we are doing now. So let's go for algorithm. The algorithm is pretty easy to formulate. So let's jump now at the example. So it's one of the examples in the end of the chapter 3F1, and it deals with some manufacturing of bolts and nuts, right? And there is some relation between how many. So you shouldn't do much more of ones compared to others. That's this line. And then there is some arrangements about the capacities, etc. You can read it, but for us to understand the algorithm is to see that here in the lines it means that we have two two parameters x1 and x2 telling how many bolts and how many nuts, and there are some relations. So the bolts plus twice the nuts should give less than 120 and so on, right? And now we want to start. So of course this is a unpleasant example to start with, because we have got this one line which I indicated already yellow, which is not coming from a standard problem. We don't like to have these minuses here, but we can easily improve it. Well, in particular we don't want to have the minuses here, but we can easily improve it by taking the minus sign for the same equation, which doesn't change much. It's here, right? So here we have 1 minus 1 and so on up to 90 here. And then what we are doing is we want to run the Gauss elimination, but not the way from left to right. We always want to find the optimal so-called pivot. So that's the thing where we want to see a 1, and the 1 will be then so the position of the 1 will be then kept unchanged, and all the rest in the column is turned into 0 by equivalent operations, right? And so if you do it here, you could just check yourself that I just take this just with opposite sign only, and then I do the Gauss elimination with the rest, and so that I get the zeros here, and this will be appearing in the other ones, right? So that's it. Now to choose the next pivot, so you see I just boxed here the positions of the ones in the columns where you have everywhere just zeros elsewhere. So this stage of this algorithm, so in this step, we can imagine that wherever we have got these ones as the pivots in columns with rather zero everywhere else, then we put always the value of these variables to be the number of the right hand side, and then you can check that the corresponding value of the optimized function will be what appears in the right slot, upper slot here. So that's very beautiful. It's absolutely fine. And what shall we do next? Next we shall try to find the next pilot. Well, here is the description. And we try to find the next pilot so that we increase this number as much as possible. And how will that happen? We simply need to compare. We need to compare what are the possible ratios, right? So here I take 30 and 3, and then 30 over 3 is 10, and this is less than 90 over 5, which is 16, and 20 over 1 is 20. So I take the smallest one, and this leads definitely to the next admissible vortex, because that's what we are doing. Just when we look at this situation, the choices of the boxed thing show us at which vertex on the polygon in the plane we are. If it was in any dimension, it would be the same. We would have some polyhedron as the boundary, and we would be on one of the vertices if we get the scheme into such a shape. And that's exactly what we want. So we simply choose the smallest one, which ensures that we stay in the region, and the value will increase, right? So, and it will increase the best way it could. And so the next one will be this one, right? So we already have these two ones. And now what about when does it end? So it ends when there would be no negative values in this upper row. So here there must not be any negative entries. So as long as there are some negative entries, it's not the optimal thing for the dual problem, because the dual problem is seen in the same scheme so that you view it from the other side, right? So here this would be just instead of this line, and this is instead of this line, and it's the same thing. So the next one will be simply, the next task will be just to get rid of this. So how can we do it? We simply choose the next pivot. So the chosen one is the circled one, right? So here I circle the 3, so there will be the new pivot. Here I circle the 2/3, and of course it doesn't matter. You don't want to handle the negative ones at all, so you compare only with the positive ones, and this will bring us to the optimal solution, which is here, right? So this is how the algorithm works, because after this third, or which was it, manipulation via the Gauss reduced echelon form procedure, we just end up with something which is already in the form where we know that it will be the optimal solution, right? So we have everything there what we need, and the optimal solution will give us the profit of 470, which is the most we can get. And you see how much we do. So we do 110 of the first kind of things and only 5 of the other one. Right. So that's it. Right, what about the correctness of the algorithm? So you see there is this ghost sign, so I will better not go into that at all, but it's, if you go through and if you have the guts to digest these things, so you see that it's relatively short. Yeah, it just needs some, say, deeper thinking about how to work with matrices, and realize that if you have this blockwise organized matrices, then the multiplication can be also understood nicely blockwise, and then you can read through these few lines, and that's it. So thanks. So I think I was this time a bit closer to a, well, not very detailed lecture, but quite long than short guidelines what to read, but it's because it's just one topic, and I thought it would be nice to do it in more or less one way, and I hope you can understand it. At the worst case, you simply can cut it into several hearings and not do it in once, right? So it's always possible to stop a video. So I will stop now and wish you a nice week.